Hello, everyone. Welcome to our first talk at CSR AI Young Achiever Symposium. My name is Han Zhiguo, and I am a second-year PhD student at the College of Information Science and Technology at Penn State. So today it is my great pleasure to introduce our speaker, Sherry. Sherry Tongshuang, who is a final year PhD candidate in the computer science and engineering at the University of Washington, advised by Jeffrey Here and Dan Wilt. She received her bachelor in CSE from Hong Kong University of Science and Technology. Her research lies at the intersection of human-computer interaction and natural language processing, and aims to empower humans to debug and correct AI models interactively, both when the model is under active development and after it is deployed for end users. Sherry has authored 19 papers in top-tier NLP, HCI, and visualization conferences and journals such as ACL, CHI, TV, CG, etc., including a Best Paper Award and an honorable mention. So without further ado, please join me to welcome Sherry for her talk.
Thanks, Hanju, for the introduction. And hi, everyone. Thanks so much for inviting me here. Today, I'm going to talk about my work, interactive AI model debugging and correction. Let's start with this buzzword, AI, and a title. So my whole line of research pretty much starts when I see AI systems try to help us everywhere in our lives. They help us on everyday tasks like setting up alarm clock, they write code with us, and they also drive our cars. But I also quickly realized as these AI systems try to help us, they also make us face some of their errors. And some of these errors are pretty hilarious, like this one on the left. I want to get up at 6:30, and then Siri says, okay, I will wake you at 6 a.m. And then it actually sets up the alarm clock at 7. So I have this 1 hour buffer of I don't know what for. But some of these errors can also be fatal, and I would definitely not want to be in a car accident caused by Tesla. Apparently, we don't want these kind of errors. So what do? We try to create better models that can make less mistakes, and better here is usually measured by some standard metrics like higher accuracy or higher F1 score. And we have improved a lot. If you see this line chart, this is basically tracking the progress of how we improve model accuracy. And each little shaped glyph represents one kind of NLP task. And blue dotted line is the average model performance across these different tasks. And then the black line is the average human baseline performance. And many of the models right now are performing even better than humans on some standard data set. But this is not going to be enough. And why is that? Let's think about this in the context of a Google translation error from 2 or 3 years ago, I think. So here we're translating from Chinese to English, and the model is correct. In both languages, it's saying Android system is pretty lagging. But when we just modify the Chinese input a little bit by switching the Chinese word pretty with a close synonym of very, this model now gets to think Android system is very fast. Yay, Android system. But if I am the developer of this model, then I will be really sad because this is something we want to catch as we develop the model, not when our model is already deployed and other people start to post this kind of errors on Twitter. So I saw many of these errors, and then I start to ask, what went wrong? And I go back and try to unpack this model development here a little bit and find there are 3 big steps involved. So when we develop a model, the first thing we do is to collect and then curate some training data. And this data is the basis of our model, but it's usually not very good and cannot really represent our real world. If we're not really careful, then maybe this very lagging version is just never in our data set. And so the data we have never really tell us how our model would behave in those cases in real world. And then we train a model, and then we move to evaluate the model. Here again, we tend to rely on some standard metrics like accuracy, In fact, accuracy is a very good representation of what we would expect from the model. We look at these two examples as a pair, what we really want to conclude is, okay, our model is not stable. It should make some consistent predictions on similar instances, but it's just not really doing that. But when we just look at this one single accuracy, then the correct example on the top will just be +1 on the accuracy, and then the arrow at the bottom will just be -1. So the model will just, this metric will just treat any correct or incorrect instance at the same level. And some of them we may care more, some of them we may care less, but because we can only take the look at this one number, so we don't really get the rich information that we want to get through the comparison. Okay, let's stare at the slides for a second and then switch our visual focus. So essentially what's missing everywhere are humans. We're not considering all of the use cases from humans and also not considering all of the expectations from humans. But we as humans, we're important. And our community is getting more aware of this fact that AI technology is made by people and it's going to be used for people. So human is the gap here, and this gap motivates all of my work during my PhD. In just one sentence, I work at the intersection of human-computer interaction and natural language processing. I design frameworks and tools to help humans interactively debug and correct AI. Some of the work is used by AI experts to validate an AI system before it is set free to act on their own. And some of them are designed to be used in real time when the end user and the AI collaborate on a problem. These nuances also bring in some unique challenges that will require me to work on some unique solutions. And just as a quick overview, first, in model evaluation, experts know what they want to inspect in a model, but they don't know how to do the analysis. So I built some frameworks to help experts make full use of their own expertise. And second, domain expertise can sometimes also be bad. When we want to learn stuff about the model or the data themselves, then our prior beliefs can actually bias us. And for this, I also built some NLP models to help compensate for what experts might have missed. And finally, end users hardly know anything about the model, and they will get even more lost when the model does not do what they want. So here I also design interaction technologies to help those people interpret and control models in real time. I'm happy to chat any of these projects offline, but here I'm gonna talk about 3 representative projects from each of these colors and dive into them. Please remember this outline because I will come back to this again and again. And now let's first get to Erudite and talk about how we can help experts express their domain knowledge and do analysis. Before we talk about how we do analysis, let's first think about why we want to analyze a model. And back to our unstable translation problem, underneath this funny example, there is something that's more essential that we want to answer. And the first is, even if the model looks really nice overall, it can still be bad on some very specific type of data. So we want to ask whether our model can really handle a data slice like A is pretty something or A is very something or others. And then second, models can be right for the wrong reason. We need to see if the model is relying on things that doesn't really matter, like whether we're using pretty or whether we're using very. But something that's fascinating about text data is, even though text is so common for everyone, at the same time, it's so complicated for AI or machines to learn, and it's very unstructured for us to do any formal analysis. We cannot really do a group by on some features as if we're just in a spreadsheet. So I start to ask, how can we build something to address these 2 issues? And here Erudite becomes the answer. Essentially, we argue that we should really rely on 2 building blocks, one being systematic grouping and another being counterfactual analysis. We built this beautiful interactive tool to make these 2 building blocks easy to use, and they look something like the screenshot. But here I will focus on the high-level idea of why these 2 building blocks are important and what they can bring. So as an example, let's see how we would use Erudite to analyze a visual question answering system. This is a task for answering questions on images. And we see this model we're analyzing is called VQA counting, I think from 2018. And this model is performing differently on these two examples. It gets how many people correctly in the first case, but it will miss how many yellowish donuts. What's your first impression on them? Well, mine is our model probably does not really know how to answer how many questions followed by an adjective. And now I want to see if this is a generalizable observation and whether I can report this problem in a paper and share it with the community. And what should I do? Let's first take a look at what the field is doing. Again, because text data are really unstructured and hard to analyze, if we read either the dataset description or the model error analysis sections in some NLP papers, they all have this shared universal method. And really, they're just different ways of saying, let's try to take a random sample of the data and manually categorize them based on what we guess to be the important similarities. And if I follow this status quo, then it's very easy. I will just count the number of how many adjective errors, and I will maybe report 5% or 5 out of 100 in my paper, which doesn't seem like a lot. But this is actually not reliable. Whatever 100 data point that we are using are usually really biased and also too subjective. And so they cannot really represent the whole test data set that we're using, like maybe 10K example or something. So instead of trusting subjective sampling, I argue that we need to scale up our observed patterns to all of the relevant instances. And this is where our first building block of grouping comes in. To make text data analyzable, we designed this domain-specific language, or DSL, for extracting different kinds of attributes from text instances. This includes very common ones like how long a sentence is, and also finer-grained ones like if the sentence includes some short phrases of adjective plus noun. In this way, if we filter on the right attribute, we can find the right instance. Here, if we select the instance of how many people, then Erudite will try to do some programming by demonstration trick and suggest possible filtering queries, like we can use how many noun to find similar instances, and also how many yellowish can be generalized into how many adjective. And with these filters, we can find about 10K examples of how many noun questions in our existing evaluation data, and another 700, 800 how many adjective questions. If we further look at these orange bars, we can see that indeed our model is performing differently on these two groups. It has a much higher error rate of 63% on how many adjectives compared to 39% in how many noun. But because this how many adjective group is just so small, we don't really notice this when we just look at the overall model performance or when we maybe just sample some error to look at. So now I can report with some more confidence that the model cannot count objects with adjectives for 60% of the time. So grouping is good because it helps us compare data slices that we might miss otherwise. But when I report this, do readers really know what this description means? We asked several NLP experts to translate how they think about this kind of text description back into our DSL queries and realized the answer is no. Experts actually make really wild, different interpretations. So some people would do what we did and search for questions that start with how many adjectives. But there are also other people that, and they would say it counts as long as there is an adjective in the question sentence, no matter where. And by asking people to explicitly write out these groups, we can find the differences in their analysis, like white is at the end of the question here. And because erudite queries are precise and reproducible, it makes the analysis more reproducible. But this is still not enough, even with the grouping. We still don't know if the adjective in the sentence is the root cause of our mistake. And so here comes our second building blocks called counterfactual analysis. And this is a set of tests on what could have happened or a set of examples for answering what if questions. And in this particular example, we want to answer if the adjective was not there, will our model predict correctly? And to do this, we will delete this adjective and change to how many donuts. Now this model can make a correct answer and say there are 12 donuts in total. So it seems we're right on this particular example. Erudite will again try to make a guess based on our deletion and try to translate our what if question into some rewrite rule. And then so we can reapply the same change to a larger number of instances and quantify the impact of adjectives as we go. Like here, we can choose to remove orange on this cat example. Obviously, after this kind of change, our ground truth answer will also change, but we can still learn some important thing even without this information. And here in this case, the model is saying there's only one cat. And by comparing this to the original prediction on the orange cat question, we know the model does not really know how to count objects because otherwise it definitely should recognize more cats than these two orange cats. So in this way, counterfactual analysis help us find cases where the model is correct, but for the wrong reason. And we know this without needing to get the new ground truth answer. And with this rewrite rule and also the expectation combined, they form this what we call counterfactual test on whether the model knows adjectives. And we can get a score for how frequently the model is being inconsistent. This idea kind of inspired me and my collaborator to write another full paper on testing model capabilities. I will not get into that paper, but basically, if you write different kinds of specific tests on different model capabilities and test these capabilities in different ways, then you can get a very nuanced performance matrix on what the model can and cannot do. Which would greatly expand beyond this one accuracy score and also expand beyond just the data you have at hand. Erudite and Checklist has moved on to make some practical impact to the field. We've seen researchers adopting Erudite to their own models. And here's a sample paper of relation extraction analysis. And I'm happy Erudite can help shape reproducible insights with the broader community. And we're also working with some people at Paper with Codes to embed checklists into their default leaderboard to help people really come with nuanced model capabilities. So hopefully I have convinced you that grouping and counterfactual analysis are both very important, and with them, Erudite can incorporate reproducible, scalable, and testable analysis. So we've been talking about how grouping and counterfactuals are useful in error analysis, but they're useful not just for error analysis, and they're actually necessary for some other development stages. Now, instead of error analysis, let's think about what we need to do when we do data augmentation. This is now almost common sense, but naturally collected data sets are not good. They have different kinds of problems or gaps in their distribution. But if we can do different kinds of counterfactual rewriting on the data set, then we can add a lot more training, a lot more signals in the model training. And this is a pretty promising direction because this is hinting that after we do analysis, it is possible for us to fix the model by fixing the data. But in this case, we just want to learn something within the data that we have or within the model that we're analyzing. And so it's not as if in error analysis where we can assume developers already have dominating knowledge about what they want to know and can just take the full lead. So I also work on different frameworks and tools to make sure we can balance human domain expertise and some inherent NLP task properties. And for example, I designed Polyjuice, which is a language model-based generator that can compensate for more diverse counterfactual generations that humans might miss. I will get into Polyjuice next, and as we will see, this is in fact useful for both analysis and augmentation. So Polyjuice mostly emerged from how hard it is for humans to do counterfactual analysis. we're biased and we have really limited creativity. For example, in our previous VQA case, to understand the impact of adjectives, we can easily remove yellowish. But most of us will probably miss some other useful changes, like we can take a different adjective or maybe change the syntactic structure entirely to ask about how many kinds of donuts. If we really think hard enough, we might be able to get them, but it will waste quite a lot of time, so we usually don't want to bother. And so here I ask, how can we collect more diverse counterfactuals that compensate for what humans might miss with less cost? And because language models, it's a family of NLP models trained on huge amount of text, they see and remember more data than we as humans ever do. We want an automated generator to help us fill in the gap. And that's how we started to create Polyjuice. At a very high level, we fine-tune a language model called GPT-2, such that given an original sentence, Polyjuice can make close counterfactual rewrites. We want Polyjuice to generate a bunch of changes per text and get some diversity. And so we try to put in some signals to drive different kinds of how and where to do the perturbation or to do the rewriting. For example, how to change relies on a list of control codes. Negation here might give us how many donuts are not yellowish or how many non-yellowish donuts are there, versus insertion might just add some other constraints and say the donuts also need to be sprinkled. And for where to change, we rely on this fill in the blank structure. By replacing yellowish with blank, we are telling the model, please only fill in this part, and then the model will generate colored or yellow. So this new counterfactual is maybe how many colored donuts are there, or it might also just delete this part and give us how many donuts. So this Polyjuice actually helped us. We did a user study with 13 graduate students, and basically we gave each of them an original sentence and also a prediction. And students can play with the model and do some manual counterfactual analysis for up to 10 times. And then they were asked to guess what the predictor will do on some Polyjuice generated examples. We saw that these students couldn't really do the simulation. And in fact, they didn't do much better than just random guessing. And this means indeed, maybe the Polyjuice generated examples are supplying some additional information compared to their manual counterfactual analysis. We tried to analyze what the students missed, and these examples actually demonstrate the two reasons quite nicely. And the first one is people tend to overfit to their own inspection. So after they already see the model being wrong on how many yellowish donuts and also how many sprinkled donuts, they will just incorrectly generalize their observation and think, oh, the model will just always be wrong whenever there is an adjective. And then they will maybe miss the cases where the model can actually answer how many yellow donuts. And then the second problem is 85% of the time, people will just do something really locally. And this means they probably will not think about moving the adjective, and they will also not really know that the predictor can actually be correct in both of these cases. And with this in mind, if you remember our earlier hypothesis, this Polyjuice result hopefully give you a refreshed view that maybe it actually depends on what the adjectives are in the sentence and also where they are. So this way, Polyjuice diversity help us do more in-depth analysis. But like I mentioned before, Polyjuice can also help fix the models through counterfactual data augmentation. So instead of asking VQA model to do predictions, we manually label a diverse set of rewrites. So we move the adjective to say this adjective location does not really matter. And we change yellowish to say, but the actual color or the actual adjective does matter. If you're asking for sprinkled things, then the label would be different. And the object obviously also matter. If you ask for a box, then you will get 0. We add these generations back to the original sparse data set. And with the label, we can now train with these Polyjuice counterfactuals. We did 3 tasks in our paper, and I will show a subset of results here. So compared to just adding the same amount of original data, Polyjuice increases generalization to out-of-domain datasets without decreasing the in-domain accuracy. Here, the original model is trained on SST2 dataset, and it's a sentiment analysis dataset for movie review sentences. And then the model trained with Polyjuice augmentation performed better on Twitter sentiment analysis dataset, and it also performed better on manually created counterfactual data on IMDb data from previous papers. So counterfactual data is useful. And compared to adding the same amount of human-created counterfactuals, Polyjuice get compatible or even better results, but we do it in a way that's much more effective in terms of labeling time, because people only need to verify counterfactuals rather than creating them from scratch. So Polyjuice is more effective. Polyjuice, together with some great work from other groups, I think successfully attracted the NLP field to really consider this theme of perturbation or counterfactual-based augmentation. Some of us came together and created this challenge called NLP Augmenter, and we got around 120 NLP experts contributing creative counterfactual strategies. And they use a lot of different resources like language model, which is a little bit similar to Polyjuice, and some other things like WordNet or emoji database. And I'm excited to see so many people using so many different kinds of models for counterfactual rewriting. So here the big picture is we designed Polyjuice as a counterfactual generator and use the context or information already in language models to help compensate for what's missed by people in a way that's cheaper than manual effort. Okay, coming back to our big workflow. Besides Polyjuice and Erudite, I also have some other work for some other development stages that I won't talk about, but we do cover many stages from analysis to fixing. So let's assume we're now good to deploy some models to end user. Compared to experts, end users know much less about the underlying model structure, but they know a lot more about what they would expect on a specific task. And as an example, I will talk about a small series of work on how I design unique interactions to support end users interpreting and control large language models. So since the year before last year, 2020, our NLP community has deployed this so-called large language models. And what's impressive about them is their ability to respond to arbitrary natural language prompts at runtime. For example, if we want to do some English to French translation, we don't need to train a separate engine, but we can just fit in the model something like, given the English sentence translated to French, and then the English sentence, and then denote the starting point of French, and then the model can just continue the prompt with the French translation. But users want to do more things than just translation. When we were working on this project, many of our users, they were Google employees, and they really wanted to use the same large language model for rewriting their short summaries into some friendly and also constructive peer review paragraphs. And their short summary might look something like this. Like Tongshuang could improve her presentation skills. She has too much text on her slides. Her presentation meanders from topic to topic without a clear structure. She also does not really engage with her audience when she presents. The model indeed can do the rewriting and it generates something for them, but this generation doesn't really match with their expectation. Here you can clearly see this paragraph is pretty mediocre. It's still mostly impersonal and also does not really provide concrete suggestions. For example, it just say you should have a clear structure in response to without a clear structure. And if I got this feedback, I would be like, well, I still don't know what to do. Now, if you work on NLP or more specifically text generator, then you probably can guess what went wrong. Basically, there is some limitations in the model structure and the model doesn't really know how to do reasoning. They start to get biased by their own generations as the text become longer, etc. But if you don't work on these, don't worry, because end users also don't know what I'm talking about. But they are the users of these models. So we need to answer this question, how can we help end users interpret and improve model outputs when they don't understand the underlying structure and cannot really change the model? And our way of doing it is to build this kind of AI chains. Basically, we try to provide some more explicit knobs to end users by breaking down an original task into some subtasks. What's the intuition behind this? If you really think about many tasks similar to this rewriting, the problem from the end user point of view is basically this task has a lot of things going on, so it's really hard to build an input to output mapping. It's not very clear how users can help the model to know what presentation problems exist and brainstorm suggestions and do the rewriting. But this mapping does exist if we make the task smaller and more targeted. So instead of rewriting a full paragraph, if we just ask for suggestions on a single problem that's not engaged, then we can get very explicit suggestions like ask the audience questions or walk around the room. And then end users can come in and say, I don't want to work around the room because I cannot do that during a pandemic. So I will keep iterating on it until I'm happy and maybe get some other things like use humor. And then if we pass this human fixed suggestion to another large language model that specifically focus on rewriting suggestion bullet points into friendly paragraphs, then we can get a good paragraph that matches with what we want. Like here, you might want to ask more questions to engage the audience. Humor always helps. And so more formally, we can solve this task in 3 large language model steps, including first, ask the model to extract each individual presentation problem. And we have 3 here, too much text, no clear structure, and does not engage. And then we use the problem as the input to brainstorm suggestions per problem and get many suggestions that people can revise. And then we use both the problems and the suggestions as input in the third step to get a final paragraph. So all of the results from previous runs get aggregated. And now this rewriting is much better. And now have phrases like, oh, your presentation was so interesting, and also good suggestions like, it might be helpful to vary picture with text. And if it were me, I would divide the sections. If you think about this, it's quite amazing. So arguably in all of these 3 steps, we ask this nice language model to do something simple. So in a way, we are repeatedly underutilizing what it can do. But by doing this, humans have more say in the process, and then the final result is also better. So this is hinting that maybe sometimes one way to improve the explainability and also debuggability of a black box model is to have it do less for multiple times, and then you get a better result eventually. We generalize this idea of chaining and build some interface for users to build their chains for different use cases, and also help them interact with their chains to achieve their personal goals. And through a user study comparing chaining to just the standard baseline without chaining, we saw our users really like interacting with large language models through chaining. In particular, they find interacting with large language models through chaining more transparent, because after this task decomposition, users were more aware of what are the things that the model can do for them. For example, one participant said, chaining helped you speak the language. It lifted up the hood and showed what's happening at different phrases. And they also feel that interacting and changing the output of each step helped them to steer the system towards their final goal. One participant phrased it as this, and I really like it. They said chaining makes it easier to fine-tune things, and too much freedom without chaining is actually a curse. One more thing that's interesting is I think this perceived transparency and controllability really encourage our end users to feel more comfortable and confident when they use the large language models. Originally, I really mostly just treated chaining as a tool for helping people with to use large language models on their own complex tasks. But then after doing our user study, some UX designer realized, oh, I don't really need to know how to write fancy instructions or prompts that make the model do everything. I can just build small function building blocks or large language model steps for them to achieve something bigger together. And they actually started to use large language models for prototyping some complex applications. In the slides, this is an example chain from one UX designer for prototyping a music recommendation chatbot. Basically, just have several branching logics to detect and handle different kinds of user commands. So if you say, play music by the Beatles, then this chatbot will know you want to play some songs and try to outsource the music query to some YouTube API. But if you ask who are the country artists, then it will go to some information search branch to give you some factual answers. Or if you say something that's totally unrelated to music, it will try to chat with you and ask what you need. So this designer was really excited because they couldn't figure out how to design the instruction to make one large language model do all of these, but they can build this multi-step chain in just a few hours. And I was also excited because I can see chaining being the bridge between large language models and end users. So AI chains can make the end user large language model interaction more transparent by helping people know what the model is doing, and also more controllable by helping users find ways to guide AIs towards their expectation. And most importantly, we achieve all of these through just interaction designs without having to change the model themselves. And that concludes the 3 examples I wanted to cover. Again, this whole line of work has been able to make some practical impact in both the academia and in industry, with the community analyzing and sharing insights and knowledge with these tools. And some of these work have also been or will be integrated into some open source AI libraries or deployed internally in the industries. And this is all very exciting to me. But what's next? Now I'm going to talk a little bit about some other exciting things that we can add onto this figure. If you remember this human is missing slides we saw earlier, the way I've been trying to add humans back into the loop is to enrich and concretize the evaluation through some data work. We either group similar data, generate counterfactual data, or semantically decompose some of our data points. So essentially, hopefully, I am on my way of creating a world of human-centered AI with data-centered approaches. And I think this is a fascinating world to be in because data is what people can easily play with, and data is also what powers all of the existing models. So it serves as a pretty nice communication medium. And to push this forward, I think there are 3 big aspects that I want to explore more. I will briefly get into each of them, but essentially they represent 3 levels of connections between humans and AI, from humans just using the data for inspection, to exchanging data with AI for some communication, to bringing our own data to AI to get some controllability. First, exploration and exploitation. This part will pretty much be a close follow-up of what I have been working on. So back to our old friend sentence. Because of how high dimensional text data is, we can generate tons of meaningful counterfactuals just on this super simple sentence. And this set of related data will very quickly explode even on toy examples. So imagine how overwhelming it will be if you're dealing with a 10-paragraph essay. But if you really think about how we do analysis and exploration, we don't try to do everything at once. We try to go through some iterative process. So basically, starting with one sentence, we might first ask if having an adjective matter and delete yellowish, and then maybe we will ask whether the adjective location matter by re-adding yellowish back at the end of the sentence, and also ask whether we can further do some negation on the adjective. And if all of these seem to do some expected things, then we move to ask some follow-up questions, like does the model performance depend on how simple or hard an adjective is? And this follow-up will then come back to affect what data we want to use in this other existing half-baked analysis. Like you can also do negation on other adjectives. And then finally, we might also try to generalize beyond this one sentence and build some connections with other sentences. Similarly, for this end user interaction with large language models, the suggestions we get can also branch out. After we get the first batch of general suggestions, if we don't want to walk around the room, then maybe the model also shouldn't make some thematically related suggestions like do demo together with the audience. Versus if we keep use humor, then maybe we can go deeper for things like prepare personal funny stories, which again interact with other branches, like you can ask audience to predict what happened when you share personal stories. So we very easily see this expanding graph, and they exist because all of the text data just really naturally have some syntactic or semantic connection to each other. And this really intrigues me and makes me want to ask, can we use some semantic and synthetic edges between instances for exploring and exploiting the data space? For example, right now our model just reacts once to human. We ask for something, model says, here you are, and then human do the selection. But if we can use these graphs, then maybe we can have the conversation carry on. So the model can further suggest things like, did you know you can also explore moving the adjective, and then also generalize to do the same adjective swap from yellowish to sprinkled as a way to follow up on users' previous train of thought without humans repeating their procedure. And this way we can track and build on previous analysis, and it becomes almost like a recommendation system for evaluation data, so that we can gradually move towards human-specific needs and establish maybe a pool of related evaluation objectives. And to make this happen, on the modeling side, we probably need to design some generators that can traverse this semantic and synthetic edges and do some data recombination in a few shot way, so that they can react to maybe a minimum number of human examples. And then on the HCI side, we would also need to design interaction technologies for making the graph traversal intuitive for humans, and to learn what kind of interactions would be more informative on which way to go onto the graph. Eventually, if we have a connected set of examples, I think it also helps us to define some finer-grained evaluation metrics. For example, we might be able to say, evaluate on this particular capability on negation using this part of data, only if we already know the model can handle this related capability on connected data points. Moving to the second line, how can we communicate with AI through data? And this comes from my experience that for almost all the tools that I built, I have to define some form of shared language. It could be domain knowledge in Erudite, or the signal on how and where to do rewriting in Polyjuice, or some form of natural language that large language models can understand. It's natural language, but it's still kind of in some format, like given blah, do blah. And naturally, we don't speak in those languages. In other words, we are always trying to climb some learning curve in order to communicate with AI. This is hopefully not surprising to people. Like most of us probably have experience talking to some chatbot or virtual assistant in really short sentences, or trying to really hit the right keyword. But the thing is, machines are also trying to accommodate to us. Some studies have found that big AIs these days actually follow nonsensical instructions the best. So for this model to classify a real joy as positive, we need some best instructions like the random, like atmosphere, a lot, dialogue, blah, blah, blah. And this becomes a little bit problematic because we don't want to add burden to both sides when we ask humans and AI to interact. And this is still in the text domain. And things become even more complicated if we distinguish more carefully what the humans, who are the humans and who are the AIs and what tasks they work on. So on the AI side, NLP model take not quite interpretable instructions, and vision model take not quite interpretable superpixels. And then on the human side, professionals might want to follow their own like normal protocol or procedure, and do not want to consider what the AI can or cannot take in as a signal. And also interesting is humans' vocabulary would change based on humans' domain expertise. This is a real story from me. I once tried to give feedback to an AI-assisted music editing tool, and they trained this model that required me to say things like higher pitch. And I can only think in the line of this should be faster or slower. So I couldn't really share the same vocabulary with the music expert on this same task. So this makes me want to ask, can we build some communication layers between humans and AI so we can more effectively exchange data with AI? And to make this happen, I think two interesting things should be, one, to build vocabulary of how humans with different levels of professional knowledge express their intentions. And this is where I would really hope to collaborate with domain experts, like from medical, education, and some other domains, just to know what people would do naturally. And two, to translate human vocabulary to model vocabulary. In NLP, we already have some search method to find those best nonsensical instructions for language models. And I think it would be nice if we can get it to extend to searching for instructions given or condition on user intention. And I don't know much for vision or robotics or other AI fields, but I would also like to work with the experts and see, like, for example, how would visual signals or voice be different or similar to text? Eventually, I think this intermediate layer can push model testing beyond general model capability and onto more specific user groups or use cases. And this hopefully will also lower the learning curve of using AIs and help onboard users to AI interactions in real world. Finally, super briefly, I hope we can also get to a point where we can better control and customize our AI system. So for the last several years, we've been trying to train a single model to rule everything. We want one language model to know grammar, sentence, sentiment, reasoning, common sense, ethics, and so on. And users basically can just use and audit the AI. And this is making our model really powerful, but it also brings some problems. Essentially, with models getting really large, they don't really learn everything effectively. They learn something better and then forget about other things. And it's also really hard to retrain models. So in many cases, we're using models to train in 2019. And more importantly, these models are also becoming really hard to customize, which is actually important considering how subjective our world is. For example, the sentence is positive if it's from me. I'm a big Harry Potter fan. I even have a paper named Polyjuice, but it can also be really negative if it's from someone else. And now just these 2 months, we're seeing a trend of asking the model to learn less. Basically, we can have some model that just know maybe grammar, reasoning, common sense, and then plug in some database to the model so that the model can get more updated world knowledge from Wikipedia, for example. I think this data plug-in direction is also quite promising for improving human agency and control. Humans might use self-labeled data to express their view on subjective tasks or ethical issues, or add some context on how they want to use the model. The most interesting thing here is, instead of following the sequential stage on the left, some amount of data collection can happen together with humans when the human is using the AI. So we just have to figure out how to allocate what data needs to be collected and what data needs to be plugged into the model and how the model should use those data. And with that, I'm happy to take questions.
Thanks, Sherry, for your wonderful talk. So do we have questions from the audience? Yes, Patron. Yeah, so I think so. I have one question, so one general question. So my feeling about the counterfactual analysis and or other works, they are mostly diagonalized. So maybe the model makes mistakes in this test case. So is there some kind, yeah, so how can the model developers use this kind of test case or know that, well, this model do wrong in this certain test case and to try to improve the model. So how can we use this kind of analysis to communicate with the model developer in order to improve the model?
So do you mean like how do we know like what kind of factual data is expressing what kind of capability, or like how human?
Yeah.
Okay.
Yeah. So my feeling is that the counterfactual analysis tries to track the limitation of the current model. So maybe is there a way so the model developer knows where the limitation is, but how can they improve the model accordingly? Is there some thoughts about that?
Yeah, so basically, I think most assumption of our work is essentially, so everything, all the analysis and fixing are basically very human-centered, but we have this assumption that humans are driving all of the analysis. So in checklist or in Polyjuice or in whatever work we do, human would say, I want counterfactuals on negation. And so that I know this particular example is for negation, or I want this particular group of example to be on synonym, or to be on lexical information, to be on coreference. And because all of these changes in counterfactual rewriting are targeted and not like untargeted, all of the example kind of implicitly represent some assumption or some capability that they should be reflecting off the model. And so when you do fixing, it's pretty much the same way. If you say like, my model does not understand coreference at all, you can add specifically kinds of examples that express coreference and say, you need to learn this, especially because maybe the original sentences that they are changing from does not have coreference. And by adding this, you're trying to pop up this signal and say, emphasize that on this part, because this seemed to be more important than others. And I think that's how we try to do try to communicate back to the model, like, this is the thing that should be fixed.
Yeah. Cool.
So, hey, I have a question. So thank you so much for coming and providing us this fascinating talk. So I'm very fascinated by your work, and I'm especially like impressed by your, like, for example, in your page 86, the page 86. Yeah, I think you did a pretty nice.
Let me reshare so that I know which pages.
Sure, 86. Thank you.
86.
Yeah, so I think you did a pretty nice job and amazing job in like organizing or grouping a set of very representative, either like patterns or some control codes or some like human problems from either the model side or the human side. For example, in your like Erudite or Polyjuice problem, you extract the patterns of the model errors or some like generating codes. Your chain work from human and curious about how to devise among all these tons of needs. Some experience.
I didn't catch that because of internet.
Yeah, let me like clarify the problem that, for example, in this slide, you did a very good job in like extracting some representative patterns from like model side.
I think her Wi-Fi is not stable.
Yeah, she just dropped off, I guess. Okay.
Hello, hi back.
Sorry, my network is like unstable. So my short question is that how did you like extract these very representative prototypes from like either models errors or like humans needs? Yeah.
That's a good question. I think it's a very interesting way of forming like this question. Like, it is true that you can pretty much do abstraction from either the model point of view or from the human point of view. Looking back at my work, I feel like most of my work tend to take the human view first. So like in Erudite, basically the way we started working on this kind of abstraction of how we design the domain-specific language or how we think about the errors is by talking to a lot of other NLP students or developers in some AI companies and see what are some things that they want to know and why they still cannot know it, and then try to abstract away from this really concrete examples to make something that's generalizable. I think this is maybe the reason I take this more abstract from human way is basically because for all the analysis and fixing, we kind of, I think human is the center of all of these knowledge of the AI systems. So it's maybe more intuitive and more essential to do all of the design from their point of view so they can come in and do things that they want. But at the same time, then I realized that models, they also need to understand something so that they can respond. And so I think I usually start with the human side and then gradually try to move and learn what are some representations in the model so that, and see how we can translate this human-centered view into the representations of models. And I think this is also a emerging view in the NLP domain. So they have this prompt tuning thing going on recently. And the way that we try to do prompt tuning is basically try to reformat our downstream tasks into model pre-training tasks. So just make whatever we want to do more similar to what the model is doing, just to make sure we are more connected to the model. So I think it's just try to pick the view of which way should be more adjusted, seem to be important.
That's very helpful. Thank you.
Do we have questions from audience? Okay, if not, so let's thanks Sherry again for your wonderful talk and coming to give our talk at Penn State. And also thanks everyone to participate in this seminar. And our next talk will happen at the February 8th. So it's about 3 weeks after. So yeah, thank you. Thanks everyone.
Thank you.
Bye.
Bye.